This is our last session in of this course, and I hope we've done an effort that will help a lot of our students, teachers, and other people in the community that can benefit from the power of statistics. We are discussing the issue or the subject of Six Sigma. And it's so interesting that right before we started recording here, I was trying to, or the director was trying to fit me within the frame of the camera, so I will not be shown off the camera or off the range. And I was thinking of the Six Sigma aspect. In a Six Sigma sitting, I should be able to move to the right or the left or feel comfortable and yet remain within the camera range. Same thing as in the example of the car or the example of a company producing cell phones, laptops, DVDs, you name it. All of these are products that have to be associated with some allowance, because if we don't allow for a room of some error, or if we don't strive to always make sure that the process is still robust and the product is still robust for some human error, and with these errors still can meet the customer specifications, then we may be dealing with a huge disturbance in the marketplace. This session here is the final session of Six Sigma and the final session of the course. So it's a little bit analytical, but let us go and finish it, and hopefully you will learn a little bit more about Six Sigma in this session. We ended the last session talking about the type A and type B shift in the process, and we actually ended up with this slide where you can see here that if the process is centered, meaning it's not deviating target wise to the right or the left, then a 3 sigma process will have a CP of 1. Of course, the CPK here is no concept, because the CP and the CPK will be the same for centered process as we mentioned before. At a 4 sigma, we will have a CP of 133. At a 5 sigma, 167. And at 6 sigma, we will have 2. That is something we have to strive for. And what's good about that is normally increasing process capability coefficient or CP value is associated with an increase in cost. That's not the case here. We are talking about allowing ourselves to deviate within the spec limits, yet increasing our CP. When the process is shifted to the right or the left, that is type A shift, we see that the CP and the CPK will be different, because now we have a target that's moving, not just a variation sidewise. And as a result, for a 3 sigma process, we see that the CP will be 1, but the CPK will be 1/2, which is less than 1. So that's undesirable, and that's a process that's out of control. Even for a 4 sigma, the CP will be good, 1.33, but the CPK will be less than 1. For a 5 sigma process, the CPK will be 1.67, and the CP, will be 1.67, and the CPK will be 1.17. For a 2 or 6 sigma process, the CP will be 2, and the CPK will be 1.5. It's very important that we understand that in a 6 sigma process, our goal is to reach a CP of 2 or greater, and the CPK of 1 or 1.5 or greater. This is very important, and that should be our target goal. Whether we achieve it or not, that goes into the management structure of our organization. Let's take an example here, practical example. In a process producing heavy-duty roller bearings, the target outside diameter is 40, the minimum spec limits is 39.6 and the maximum is 40.4. We gave you examples similar to this before when we were addressing the process capability ratio. Now suppose that the process data indicates, these are the real data now, indicates that the actual mean diameter is actually 40.2 and that the standard deviation is 0.1. Well, this is a straightforward CPK question. How we're going to connect it to Six Sigma, we'll see that very shortly. We first calculate our CP value. And we know that the CP is upper spec limits minus lower spec limits divided by 6 sigma. We've done that in previous sessions. Our upper spec limit is 40.4. The lower is 39.6 divided by 6 times the sigma of the process 0.1. And now we have a PCR of 1.333. But there is one catch, and that is the process has actually deviated from the target. The target was 40, but the actual mean is 40.2. And in this case, we have to use the K value. We have to use the CPK. And the K is target minus the mu actual divided by 1/2 times upper spec limit minus lower spec limit. We covered that before in previous session. And now we see that the K is 0.5, leading to a CPK of 0.6666. So this is a process that is capable by the definition of CP, but is totally incapable by the definition of CPK. So by comparison with the values here is that the CP and CPK values of the process indicate that it is really a 3 or plus or minus 3 sigma process. Okay, in other words, this means that the process is likely to produce more than 66,000. If you recall, 811,000 defects per million that was associated with the 3 sigma process. The reason for that is we have quite a shift in the process center. So at these values here, if you use this table, you're going to find that here is the value or the values of CP, CPK that fit this example. We have a CP of 1. We have a little bit higher than 1, but look at the CPK, it's 0.5. Now the next level would be 0.83, which is the 4 sigma. So we are more than likely at the 3 sigma level. Let's look at this by a graph here. Here is the process, okay, the normal process. Now it's a center of 4. Now that's what we thought. Our spec limits are here, 39.6, 40.4. But when we tested the process, it turned out that the process center has shifted from 40 to 40.2, as you can see here. So this red distribution here represents the shifted process. So as a result, we have a shift from the target, okay, which we calculate by 1/2 times upper spec minus lower specs minus the actual mean minus the target. So all of this is 0.4. All of this, the shift in the target value from 40 to 4.4 is from 40 to 40.2 is 0.2, and that gives us a D0 of 0.2. Okay, now what does that mean? It means our PCR is 1.33, our CPK of 0.66, and we just calculated these a minute ago. So it's very important that we understand that when there is a shift in the target and there is a wide shift or sidewise shift, then we're going to have to, we will deviate from the 6 sigma, and we may be falling under the 3 sigma process. Very good. Here is another example. Suppose that in the process producing the heavy-duty roller bearings described in the previous examples, efforts were made to recenter the process. So we're going to take the center of the process back to 40. Well, in this case, the CP will be upper spec minus lower spec divided by 6 sigma, which is great. That's not going to make a difference because the CP does not account for the shift in the target. But the K here will be 0. Why? Because the target value minus the actual mu is now 0. So as a result, the CP and the CPK are above 1, 1.33, and guess what? Now we're dealing with a 4 sigma process, not a 3 sigma process. So as a result of recentering or going back to the target center of the process, we were able to move a process from a 3 sigma to a 6 sigma process. Keep in mind that in many situations we have to know both the shift B and the shift A values corresponding to the shift in the process or the sigma of the process. If we go back to the previous example, we see that in the first case we really had about 66,000 defects as a result of the shift in the center from the 40 to the 40.2. So that's an 0.2 shift in the process, and at 0.1 sigma, I think it was 0.1, yes, 0.1 inch sigma standard deviation, we have 66,000, more than 66,000. When we recenter the process, we took it back to its normal, we reduced the process. First we moved from a 3 sigma to 4 sigma, and that resulted in reducing the defects from 66,000 down to 63,000. These are practically proven techniques. These are not theoretical issues. These are real issues that if you strive to improve quality, you will definitely reach the required or desired target. Here is another example. Suppose that in the process producing heavy roller or heavy-duty roller bearings described in the previous examples, efforts were made to reduce the variability. So now, from a standard deviation of 0.1, we're going to even improve the process further and go down to 0.065. Now, if we repeat the calculation of CB and CBK, can we move the process now? Remember, the process started at 3 sigma because of the shift in target. Then we took it down to 4 sigma because of the recentering the process. Now we're doing further improvement by reducing the standard deviation from 0.1 to 0.06. Now, if you start with the uncentered process, here's what you're going to get. The PCR will be 2.05. Keep in mind, this is 6 sigma, now 6 times 0.065. So that's much better than the 1.3 that we had before. The K is still going to be 0.5 because we have a shift in the process, as you know. But the CPK is now, instead of being 0.5, it's now 1.026. That improvement in the CPK was primarily a result of reducing the standard deviation from 0.1 to 0.65. And now we feel that we are at 4 sigma or better. Now, if we center the process back to the target value, repeated the calculation, here is the PCR is now 2.05. Goodness, that's almost a 6 sigma. Indeed, it is. Here is the K, which is 0 because there is no difference between the target and the actual. And here is the CPK, which will be identical to the CP. So now we're dealing with a 2.05 PCR, and that is indeed a 6 sigma process, because if you look at the 6 sigma, we have a CP of 2.2. We have here a CP of 2. We have here a C of 2.05. So that's definitely a 6 sigma. And we don't have to worry about the CPK because the process is not off center. As I mentioned before, 6 sigma is about management as well as analytical. We have to define. And when we say define, we define our quality problems, the causes of defects, and we can use the problem-solving techniques that we discussed in previous sessions. But defining is one issue, and the measuring is another. If you cannot express the quality issue in a quantitative fashion by measuring that, you will not be able to solve the problem. And if we can express it in quantitative fashion, that means we can analyze it. And if you can analyze it, then hopefully you can improve and control. It's very important to define your opportunities first, or define your defects. Secondly, to measure it. Thirdly, to analyze it. Fourth, to improve the quality of product or service. And the fifth, step would be to control or maintain the momentum. Let's take it one by one. Define the opportunities. Define your opportunities. Well, there are many opportunities of reducing defects. You can reduce defects in many different ways by seeking these defects, where it is located, how can we reduce it, and hopefully try to seek ways to reduce these defects. Okay, so that's the first step. Define the opportunities. Some Six Sigma experts define an opportunity as the lowest defect noticeable by a customer. Well, that's a good definition. In fact, this definition is debatable sometimes, but I don't think it's a bad one. It's the lowest defect noticeable by a customer, and the customer is always right. Typically, most products and services have more than one opportunity of going wrong. Apparently, some manufacturers of large complex equipment with many components prefer to count more than one opportunity. This means that there is a great judgment involved in or involving organizational personnel based on customer views on what should be considered as an opportunity. So defining the opportunity has to come in view of how the customer see what the defect is. Then define your defects. Well, defining what a defect is to your customer is a critical aspect. It's not an easy one. You need to first communicate with your customer. And that is where the management aspect of Six Sigma prevails. Via focus groups, surveys of how your customer feels about the product, or other voice of the customer tools. To Motorola pager, for example, customers, a defect was defined as a pager that did not function properly by the judgment of the customer. If you are in a school, a defect may be defined as the students who did not make it through the school, not because of his or her inability to learn, but because of a deficiency in the support system by the school. In a hospital, a defect may be defined as failure to cure, not because of inability to do so, but rather because of misdiagnosis. For a power company, a defect may be defined by the customer as 1 minute or of no power. Can you imagine 1 minute of no power, what damage that can cause in millions of dollars across the country? In some countries, people stay without power for hours. So you can just imagine the disaster as a result of that. Then we move to measuring the opportunities or defects. Now that you have clear definitions of what an opportunity and defect are, you can measure them. You may need to set up a formal data collection plan and organize the process of data collection. If you're talking about a school system, for example, the passing rate, the retention rate, the transfer rate, and so on, all of these are measures of opportunities or measures of defects. If you're talking about a restaurant, the customer return rate, how often the same customer comes back to the restaurant. In manufacturing, the rejects, the defects, all of these are measures of opportunities or measures of defects. Step 4 is to calculate the yield, and that's very important. How an organization calculates process sigma is based on calculating the yield. And what is a yield? A yield is equal to the percent of this ratio here, which is the number of opportunities that you have to reduce defects minus the number of actual defects divided by the number of opportunities. Very simple definition that gives us the yield. And if you can calculate that, and we're going to show you that by example in a minute. If you can calculate the yield, you can refer to the process sigma yield tables, and these are very, very useful tables. Look at this. What we have here is the yield. I'm going to show you this by example in a minute. And at different yield values, you can detect where you stand as far as the 6 sigma or the 5.92 sigma or the 4 sigma and so on. So you can see based on the yield percent, you can determine what level of sigma you are 3 or 4 or 5 or 6 sigma, you can also determine the defects per million opportunity. Notice that at the 6 sigma, you have a yield of 99.9997. We calculated that from the area in the previous session. And you have 3.4 defects per million. We also calculated that. And what was the area then? That was the yield that we just gave you the equation for it. Very good. And you can move on and on. Here is the 3 sigma, for example. You have 93.32 yield percent. You have a 3 sigma process, and you have 66, almost 67,000 defects per million. Let's take an example. Suppose that in a process producing memory cards, 4 out of every 1,000 cards do not conform to specifications. And we need to determine the process sigma. Because an organization needs to know where they stand. What is their process sigma? Well, that's easy. We can calculate the yield. And how we calculate the yield? Well, the defect rate here is 4 out of 1,000. 4 out of 1,000 is 0.004. That means we have a defect rate of 0.4%, which is, by the traditional wisdom, that's not bad. 0.4%, it's hardly any in a 100 units. But if you go per million now, and multiply that 0.004 times a million, now we're talking about 4,000 DPMO. That's 4,000 defects per million opportunities. Now that's huge. And if we calculate the yield corresponding to that, we have a 1,000 opportunity. That's the 1,000 cards, minus 4 that are out, divided by 1,000, and that gives us the yield of 99.6%. Now remember those tables? If we go back to the tables, now that we know the yield, which is the number of conforming units per total number of units, going back to the table, you will see what does that correspond to. Now before I do that, look at this. Here is our area, the 99.6%. Here is our Z value. So we can find the Z value if you don't have the table. Because if you find the Z value at area of 0.996, as we learned in the statistics lessons, we see that at 0.99598, which is the closest value to 996, we have a 2.65 Z value. Now remember the shift in the process by 1.5 sigma. That was the common theme or the threshold of 6 sigma. So that 2.65 plus the 1.5 sigma, which is what the process is allowed to do, will give us a 4.15 sigma. And if we go to our table now, we find that the 4.15 or almost 4.2 correspond to, here is the yield that we just calculated. It corresponds to about 3460 or 3,460 defects per million. And then you can go back and try to reduce your yield, reduce the number of defects, improve the quality, or do other things that can improve your status. Okay? Here is the example. In summary, we have the yield, we have the percent we just calculated, we calculated the Z, we added that to the 1.5. Now we can calculate the CP, by the way. And how we calculate the CP, or the process capability? It's very simple. We have 4.15 sigma process. We divide that by the 3 sigma, which is the span, and that gives us 1.38, and that is the process capability ratio. And that simply means that this process, although it has 4 defects per million, or it has a large number of defects, 4,000 per million defects, but still capable by our traditional definition of CP. In fact, you can see here that this is about 4 sigma process. Why? Because this is about 1.33. Now remember, we don't have a shift in center here, except for the 1.5 sigma. Back to our work here: define, measure, analyze, improve, control. These are the concept of 6 sigma. As to recall what we said, a 6 sigma is a measure of quality that strives for near perfection. You may not reach it, but you need to strive for it. It applies to all kinds of products and all kinds of service, from education to hospital to manufacturing to restaurants to products making. It's a disciplined, data-driven approach and the methodology for eliminating defects. And that wrap up our session of Six Sigma. In summary, it is an approach that is twofold. Management approach to encourage people to reduce defects via the black belt and the green belt approach that we discussed. And it's also an analytical approach, because any attempt to improve product will have to begin by actually measuring where we stand, what's our status. And that measurement can be by first measuring our process capability ratio, or if we are shifting to the right or the left, is by measuring the CPK. And if we can measure that, we will know what sigma status we are in, and also by measuring the yield or the opportunities minus defects divided by opportunities, and that will give us a good idea of what percent of defects we have and how far do we need to go in order to reduce these defects. This wrap up the entire course of statistics. It was a pleasure doing this course, and I hope that as many people, students, faculty, and other audience will learn from this. Of course, within the 46, 47 sessions we had, we covered a lot, but nothing is ever enough. We can cover more, we can talk more about statistical applications, about quality control, about SPC, about Six Sigma, but the best we can do here is to at least steer your thinking in the direction of using statistics at a larger scale in whatever the applications that you are using. Thank you.